In the next lecture, we'll go into encoding a lot of information efficiently using binary numbers and also manipulating that information using binary operations. But first, I'd like to talk about simply counting in binary. So we know how to count using decimal numbers. We start with 1, and then 2, and 3, 4, and we go on in the ones place until we run out of numbers, right? We only have the numbers 0 through 9 to deal with. So once we get to 9, we can only count 9 things. But we have this trick where we can add a number in the tens place, and we go to 10 and onward, 11, 12. And if we run out of numbers, we get to 19, then we can say, okay, I'm going to increment the tens place, and we can go to 20. And when we get to 99, we say, okay, I'm done. I can only handle 99 numbers. Not true. I can just add another place value and go to 100. And in this way, we can actually, fortunately, count an unlimited number of things using decimal. You may have heard that computers think in binary. Everything's encoded in these zeros and ones. Binary works just like decimal, except that instead of having the digits 0 through 9 in our toolbox, we only have the digits 0 and 1. So if we're counting, we can start with 0, and then we count our first object, but then suddenly we're already out of digits. So what do? We go to the next place value. So this is 0, this is 1. We're out of things that we can count. In decimal, we went through 0 through 9 and went to the tens place. In binary, we go 0, 1, and then we go to the twos place. So we put a 1. It looks like the number 10, but it really represents the number 2. And then we go on, and a 1, 1 in binary actually represents the decimal number 3. 1 in the twos place plus 1 in the ones place gives us 3. Now again, we've already run out of digits. We have a 1 in each of our place values. So just like decimal, we go on to a new place value, which is called the fours place in binary. We put a 1 in the fours place and reset the twos place and the ones place to 0. So this number represents the number 2 in decimal. This represents the number 3. And this represents the number 4. And on we go. 5, 6, 7, and 8. Usually we indicate that we're using binary by filling to the left with zeros. So instead of 0, we'll actually write maybe 8 zeros, which is called a byte. So that would represent 0, and then if we wanted to go to 1, and so on. And the reason we represent this with 8 digits instead of just the 1 digit that we need is because this is the way that early computers actually stored binary information in groups of 8. And they would actually represent whether tiny electrical switches called transistors were either turned on in the case of a 1 or turned off in the case of a 0. Let's talk briefly about converting from binary to decimal and from decimal to binary. You don't really need to know that for this class, but it'll motivate a discussion of why we would use this really complex system when we already have a decimal system. I have no idea what this number is going to end up being, but we have 8 binary digits, 1, 2, 3, 4, 5, 6, 7, 8. That makes up a byte. And let's note at the top the place value of these digits. So remember that the rightmost place value is 1, just like in decimal. The second is 2, this 2's place. The third is 4, the 4's place. And let's note for a second that this is actually, we're in base 2. So this is 2 to the 0 power, 2 to the first power, 2 squared, 2 to the third power, 2 to the fourth power, 2 to the fifth power, 2 to the sixth power, and 2 to the seventh power. So we call this the 128th place. Now, to convert this number into decimal and see what this represents as a decimal number that we're more familiar with, we just add up the place values where we see a 1. So we just consider these to be on. So we say the 128th place is on, so we'll add 128. The 64th place is not on, the 32th place is not on, but the 16th is, so we add 16. We add an 8. 0 4s and 1 2. Okay, we'll add up all these digits. 8 and 8 is 16. 16 and 8 is 24. Add these up to get 5. And we find that this binary number 10011010 represents the decimal number 154. We want to be able to go from decimal to binary as well. It's a little more complicated. This time we need to decompose a number into powers of 2 that'll add up to that number. So let's say we're going to take the number, let's say 107. And we ask, are there any 128s in 107? Can we fit 128 in 107? And we can't, so we're going to put a 0 in the 128th place. Now we can fit a 64 in here in 107, so we're going to put a 1 in the 64's place. We'll subtract 64 from this number, and we get 43. We can fit 32 and 43, so we're going to take out a 32, subtract, and we get 11. We can't fit a 16 and 11, so we'll put a 0 there. We can fit an 8, subtract 8, and we get 3. So we subtracted 1 8. Let's move that 3 out. Well, we know from 3 we can't fit a 4, but we can fit a 2 and a 1. So the binary representation, and we can say 0b as an indication that we're talking about binary. 0b 0 1 1 0 1 0 1 1. So the decimal number can be represented in binary as the number 0 1 1 0 1 0 1 1.